Hello, in this video, I'm going to give a walkthrough of my eighth collab, which is PyTorch Advanced Concepts collab. And yeah, let's go ahead and start running the cells. In the first code cell, I installed the WAN-DB library, which stands for weights and biases. It's used for later for experiment tracking and logging training sets. Next, I would run this cell where I set the seed, I set the random seed, and for reproducibility, and I also inquire all the required libraries which we can see here, and I also define the GPU or CPU depending on availability. I also get the global configuration values like batch size, num classes, and input dimension for fashion MNIST task. Next, here in this cell, I load the fashion MNIST dataset using Torch Vision. Then I normalize the image values to range from 0 to 1. And I split the original tracking set into training validation set and keep smaller subset for faster experimentation. After that, I flatten each image into 784 dimension vector for creating PyTorch data loaders for training, validation, and testing. Next, I would run this helper function. This function calculates accuracy from logits, evaluate a model on data loader, plot the training history, summarize one experiment, and compare multiple experiments in a table. Next, I would run this cell here. I define the baseline multiplier perceptron for classification. Then I create a standard PyTorch training function. Then I use a cross entropy and Adam optimizer and logs training and validation loss accuracy across epochs. So these are the reference tables and graphs we can see. Next, in this cell, I define a custom classification loss called custom Hubbard classification loss. Instead of standard cross entropy, this loss compares the predicted class probabilities with one hot target vector and applies a Hubbard style penalty, which is quadratic for small errors and linear for large errors. Then here I define a custom building block for the advanced model. First, I create a custom Gaussian noise layer that adds noise only during the training. Then I define custom dense layer called myDense, usually manually created trainable weight and bias parameters. After that, I build advanced model using these custom layers together with layer normalization and dropout. So this is the main advanced training cell. Here I define a custom momentum optimizer from the scratch, a simple cosine learning optimizer from scratch, rate scheduler, and a full custom training loop. The training loop uses the custom Hubbard classification lots, adds manual L2 regularization, tracks training and validation metrics. So we can see after that, and then here in this cell I train the advanced model using the custom training loop defined earlier. I also provide the tensor board log directly so the training metrics can be recorded after the training. I plot the learning history and inspect the final rows of the history data frame. This is the data frame. Then I would launch the Tensor board, very interactive one. And Tensor board helps visualize the log training and validation metric from advanced PyTorch training run. So we can see that how it helps us visualize so well. Like, yeah. Next is here I initialize weights and biases run in offline mode and store the basic experiment setting like epochs, batch size, dataset and framework. Then I train another advanced PyTorch model using the same custom training loop but the same time WNB logging enabled. Next, in this cell, I compare the main experiment in a summary table. This includes the baseline PyTorch MLP, advanced PyTorch model, and advanced model with weights and BIOS logging. Next, in this final code cell, I visualize the experiment comparison using bar chart. The chart test accuracy, compares best validation accuracy, overfitting gap across the different PyTorch workflows. This gives a clear overall conclusion of how the advanced custom PyTorch pipeline performed compared to the baseline. So overall, this notebook starts with a standard PyTorch baseline and then builds an advanced workflow using a custom loss, custom layer, a custom optimizer, a cosine learning rate scheduler, a custom training loop, tensor board, and weights and BIOS logging. Finally, all experiments are compared using metrics and visualization. That's it with this video. Thank you.